Okay, we are recording. So here is our page. Oh, sorry, you're seeing the structure view. So we have this grade scope now, which is where you're going to submit problem sets. For some reason, like when we connect it to Blackboard, I have to put it like here instead of like here. So just look for that over here. And I'll talk about that. I might just like take a break in the middle to do some stuff with like grade scope and LaTeX, that math typing software. Just so we can just, get used to these things, how everything's going to work. I also put a LaTeX resources here, which we'll look at. And here is, I sort of just posted this little outline of what we're going to talk about today, specifically logic. And we'll talk about how to build truth tables and how to do these like logical connectives and all this stuff. And that's the main thing I wanted to hit today, because like the problem set also is a lot of it's about logic. And again, I'll talk about the text source versus the PDF, but here is the PDF of the problem set. And there's a couple problems from the textbook, but and then there's a couple, like I think I promised you this would be on the problem set. And then we'll talk about truth tables today and about implication, which is what this symbol is, so that you guys could actually do the problem set. Yeah. Okay. So I want to dive right into
just wanted to check real quick. Is the problem set due on Tuesday or Wednesday? Because I know it says February 2nd. Just wanted to check.
Oh, that's not you're right. Tuesday is I think because I saw February 1st here and February 3rd here, my brain just typed February 2nd.
Yeah, no, I mix this stuff up all the time. That's why.
No, good. No, that's a good point. Thank you. I will change that.
Okay, thanks.
In fact, wait, let's see how good I can be about this. Oh, it changed. Okay. It has changed. Thank you. Yes. That's a nice thing about this program I'm using, is I can just change it on my end and it changes automatically on the web page. So, okay, thank you. Yes. So it's due Tuesday. Also, there is, I think I put a built-in grace period on. There's like a late, it says like late, but it's like, it's not going to count as late. But I did put a built-in grace period to like Friday at 5 p.m. on the problem sets this semester, so that like, if you're just having a bad week and you can't get it in by Tuesday at 11, no harm, no foul. I think it's good to keep ourselves on that schedule, but I do like to build in some like, if you start using the grace period every week, I'll start to be like, what's going on? I'll talk to you, be like, what's going on? Like, can we get back on schedule? But if you have certain weeks where you just need a day or two extra, then that's going to be fine. I know the graders like to grade over the weekend often, so I wanted to have it, so it has to be in by like Friday at 5 p.m. But yeah. But okay, so we'll talk about all of that. And let me jump on the iPad here. And then I'm going to share. Sorry, it's taking many more. Yeah, let me, I'm going to just, basically, I'm going to talk about logic for a while. I kind of feels like there's like, well, Tuesday, I was sort of just rambling on philosophically about what proofs are and, and all that. And then this example, this one proof. But today I want to kind of just jump into logic and kind of do like a quick and dirty logic lecture, just to get you guys used to some of the like language and stuff. Hold on. See if I can make this actually work. Oh, wait. I'm just seeing a black screen on my end. Oh no, there it is. It's okay. Oh, right. Okay, so yes, logic. So I think I made a comment on the class meeting page for today that, and I think I made this comment on Tuesday also, that this is not a logic course, so we're not going to like go really deep into all the logic stuff, but we just need what we need, what the kind of logic we need to be able to do math, right? So, and so what that really means is like we have sort of mathematical statements. Or really just, you could, any kind of logical statement doesn't necessarily have to be mathematical in nature. But like, you know, for example, 9 is odd. It's a mathematical statement. 9 is prime. Is a mathematical statement, which is a way of saying that not all mathematical statements have to be true. You know, it can be a false statement, but we've already seen statements like for every a in the integers, a times 0 equals 0, right? That's a mathematical statement. And there's other things you can get into, like this sentence is false, which is a fun one to try to wrap your brain around. You guys seen that before? Because if it's true, then it's false. But if it's false, then it's okay. So it's an interesting, I kind of like that one. Yeah, and so, right, so like we can assign truth values to these, right? So this one is true if we define what the word odd means. This one is false. This one is true, we proved it, well, at least from assuming some axioms. And you know, maybe it's neither true nor false. It's an interesting question. So mathematical statements can be true or they can be false. There's a little bit of a question of like what the words true and false mean. And the book, I noticed, just like looking over the book yesterday, like it sidesteps the question and just says, we won't define what these words mean. So I'll just say a couple things, which is like true could mean, I guess let's see, could mean derivable from axioms. That's kind of what we did, right, with the a times 0 equals 0 proof, is that it's like it's something that we can use logic and derive from axioms. There's another sense, it could just mean not false. Which is a little bit of a strange thing to say, but it's like false. There's something I always like kind of stumble on when I start to think about this stuff, or like I still have to like think through a little bit carefully, which is that if you want to demonstrate something false, you just have to like give a counterexample. You know, like for example, every prime is odd. Every prime number is odd. This is false because you can provide a counterexample, right? Because 2 is prime and 2 is not odd. So this is a counterexample. And so the easiest way to show a mathematical statement is false is to provide a counterexample. And if you can't provide a counterexample, well, you don't necessarily want to say it's true yet, right? Because it just means you may not be able to prove it. But there's a weird thing, and we're going to see this in these truth tables we're looking at soon, which is that empty statements with no content are actually considered true, which is like a strange thing to say, but like, so I'll just sort of say something about that. Like, if we can't, so, and I'll give you some examples of this, empty statements are considered true. And that's a little bit of a strange thing to say. And I'll have to give you some examples of this. I'm not sure why I'm writing true and false in all caps every single time I write. It's not like a usual thing. I'm just doing that. Like, let me give you an example. Like, every time I go to Mars, I am greeted by little green aliens. This is considered an empty statement because I've never been to Mars. So can we say this false? It's only false if it's like again, like false if you can like provide a counterexample. Like, can you show me a time I went to Mars when I was not greeted by little green aliens? I bet you cannot demonstrate to me that I've been to Mars and not met little green aliens, right? So like, it's a kind of like, we don't want to call this false. And so in that kind of thing, it's like the way that logic works, and I'll show you in a second, in a minute, but we don't want to call this false. So we sort of default to true in cases like this. It's a little bit strange, but it makes the logic work. It's not false until I go to Mars and it's not, and I'm not greeted by little green aliens.
Quick question.
Yeah.
In order for something to be true, does it have to follow both of those requirements, both of those definitions of true, or just one?
Oh, you mean up here?
Yeah. And if it has to follow both, then could you derive from axioms that every time you go to Mars, you're greeted with little green aliens?
Well, you could, right. I guess what you would say is like, I meant this more as like an or, not an and. Like, this could mean derivable for axioms, or it could mean not false. Like, which one, and there's just some weird things in math that math works better if you sort of take these sort of empty statements and just kind of like default them to be true. Because if it's derivable from axioms and you're assuming the axioms are true, then the statement we would definitely want to call the statement true. So like, I guess you wouldn't need both. You would just need the first one. I would say you wouldn't necessarily need, if you can get the first one, then you don't really need the second one. In fact, if you did the first one and you also showed it was false some other way, that would mean your logical system was messed up, or like your axioms are messed up. There's something contradictory in your axioms, right? So it's a good point. Like, right, the axioms need to be self-consistent, or else. So maybe in that sense there is an and here. I mean, yeah. I just sort of I wasn't really intending it that way, but it's a good question. Like, and we can easily get into this whole like deeply philosophical discussion about like what is truth and what is false, what is true and what does false mean. But yeah, I'll show you some more examples to like. And when we look at the truth table for implies, the implication symbol especially, like it's going to be kind of interesting. It's going to be kind of be the right thing, but it's always, I always have a little bit of trouble like explaining why, because it's not intuitive, right? So, okay, good. Yes, please, more questions. Questions are good. Thank you. I think that was Colin. Yeah. Awesome. Okay, so we have these mathematical statements, right? And we have this sense of what true and we have some sense of what true and false means. But now I want to talk about sort of how do we build new mathematical statements from old ones? Because it's kind of what we were doing with that proof in the last class. But there's sort of more basic stuff. So that's yeah. So that's how do we build new mathematical statements from old? And a lot of these are like logical connectives. We use logical connectives. Like and or not. Those are the three super basic ones. And then implies also is going to be one of these, but we'll have to talk about what that means. So yeah, maybe I'll actually just include that in the list. Implies. Because I want to talk about each of these in turn. So and is just like, so what thing I'm going to do a lot here is we're going to have like P and Q are stand-ins for mathematical statements. Right. And so we have P and we can think about P and Q, which is only true if P is true and if Q is true, right? If Q is true. Okay, so that's not exactly hard to think about, but oh, by the way, notation books and stuff often write, you know, I think our textbook writes P like a caret Q, you know, like this right here. Oops. Trying to be fancy and do something like that, like change the color of that. Okay, so the book will write something like a little caret, and if you take like a logic class, like in philosophy, it's like all these like crazy symbols. I actually just like to write the word and because it's like not that hard, and it reminds you what it is. You don't have to remember like the caret is and then there's a little V shape which is or. So I tend to just write out the words. So I want to use this to illustrate the idea of what a truth table is. So truth table. So we can think of a statement like this as either being true or false, right? So that's like a possibility. Q is either true or false. And if you want to think about all the possible combinations, if you have two statements, they could both be true. One could one could be true and one could be false. P could be false and Q could be true, or they could both be false, right? And so what we end up doing is we end up writing something like the following. We'll say, we'll make a table like this. So P and Q. And so I need to do all those four possibilities. So true, true is a possibility, true, false, false, true, false, false. Those are all the possibilities, right? See that the gallery's blocking my view of this. Okay, and so you can just fill this in because we using this idea up here, right? So it's basically only true if P is Q and Q is true. So we get, you know, true here, and all the other possibilities are false. Does that make sense? This is called the truth table for and. This is the truth table. Okay, fair. Any questions about that? That's just kind of like the basic, like the most basic truth table. So if we want to talk about a mathematical or, now here's where it starts to get slightly interesting, because or can mean different things. Or can mean either P or Q, but like not both. But mathematical or is actually what's called inclusive or. You may have heard the term exclusive or XOR. Mathematical or is, quote, inclusive or. So, so P or Q is true if either P is true or Q is true. Oops. Or Q is true or both. I mean, that's kind of what I mean. Like it's either one. Okay. So the truth table for this then is looks like the following. Making the nicer lines and notability. Like if I hold down. Oh no, it never works. Notability is like if you do this and hold it down, it's supposed to straighten out. There it is. It's really not worth wasting the time, but at least when we're together. Okay, so so again, you know, one way to read this up here, like I've made all 4 possibilities, but a way to think about it is like this is TTFF and this is TFTF, and that'll give you like all 4 possibilities if you just do that, right? Actually, I think our book does FFTT and FTFT, which I don't know, it's just the way I learned it was. So these may be upside down truth tables compared to the ones in the book, but sorry about that. But so now this is almost always true. The only way it's false is down here if both are false, right? Otherwise, it's true in the other 3 cases. Yeah. There is what's called exclusive or, XOR. I'll just put it down here. That's used a lot in like computer science and stuff. And so this one is, it's basically if one or the other is true, but not both, right? And so it's if they're, yeah, so this is actually considered false. So the truth table looks like that. Okay. Yeah. Then there's also like or is pretty easy. I'm not or, we just did or. Not is pretty easy. Basically, not is if something's true, if P is true, then not P is false. And if P is false, then not P is true. Oh, by the way, I forgot to say up here, the notation for P or Q, sometimes that you'll see is like P wedge Q. So the little V. So V is, the little V is or, and the little caret is and. But again, most of the times I'll just write out the word. It doesn't take that much more effort. So yeah, sorry. So we have not. And this, it's really just, since it's just about one statement, it's not about combining statements. This I actually tend to write the little squiggle. It's, you could write, I guess I could just write not P if I wanted to, like not P. So if P is true, not P is false. And if P is false, not P is true. And again, this is often written not P, like with a little squiggle. Again, there's other notations. I mean, I've had students in the philosophical logic class come talk to me and start writing on my whiteboard, and it's like, looks like gibberish to me because the symbols are totally different what they use in that class. So, yeah. But any questions about that so far? I mean, a lot of this is just definitional. So what you can do then is you can start chaining these together and like making more complicated truth tables. So anyways, hopefully I'm not scrolling too fast through all this, but I think this is hopefully fairly intuitive. Before I talk about the imply symbol, which is really the interesting one, so more complicated expressions, we can build them, right? So like, for example, what if we wanted to know, like, say we had P, Q, and R as three different statements, right? So what if we wanted to do something like P and Q, or P and not R? Look, I just violated my thing and used the symbols instead of the words. P and Q, or P and, I guess I would put not R like that. So I'm just trying to, I mean, I guess maybe these symbols are useful for like shorthand and stuff, right? So what if I wanted to find, like, what's the truth table for that? Like, what combination of P, Q, and R being true and false makes this true? So now we can build the truth table. And now we have three statements. So we have P. Actually, maybe this is a good time to do the fancy lines. Hello. We have Q. And we have R. And now, what are the possibilities here? So how many possibilities are there with three statements for all the true false combinations? Somebody tell me.
8.
It's 8, right? If I have three choices, if I have two choices, it's like 3 light switches, like one light switch for P being true or false, one for Q, and all the different combinations you can have is like there's 2 choices for this, 2 choices for this, 2 choices for that. So it's 2 times 2 times 2. Again, you can sort of systematically write this down by going like something like this: true, 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 false, 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 true, true, false, false, true, true, false, false, and then true, false, true, false, true, false, true, false. And I think this will give you all 8 possibilities. Maybe that's obvious to me because I've done it a million times, but right, you get every, it's sort of, if you just kind of do 4 trues and 4 falses and then do 2, 2, 2, 2, and then do all the individual ones, I think you get like, yeah, all the different possibilities of true and false there. Okay, and then if you want to actually build the truth table, you kind of have to build it in steps, right? So we could make a P and Q column. Right. I guess we need a not R column where we negate everything in R. We need a P and not R column to combine those. And then we need to OR these 2 columns together So you can sort of think about how you would build up to this. Again, this is pretty artificial right here because we're not even, I haven't even given you statements, but when we start doing things with implication, there's going to be important truth tables we're going to build. So P and Q, we said, actually, maybe I should let you guys try to fill this in for a few minutes rather than just talk at your faces. Take a couple minutes and try to start filling this in, like fill in this column. Like you should be able to fill in this column based on just what the each P and Q possibility is, right? And then you should fill in this column by just negating everything in this column. And then you can do this column and then, yeah, see if you can build up. And you'll get some combinations of trues and false. Wish I could play like Jeopardy music or something. Just gets uninteresting for me at some point. Just, I mean, for you guys to just watch me fill these in. If you have questions, feel free to ask either, just straight up ask or put in the chat or something. I may be being obtuse in some way that I'm not realizing, and this is very confusing, but you should be far enough ahead of me that I can probably fill in this first column. So oops. True and true is true, true and true. Everything else is false, is that right? Not R. It's just sort of flipping all the false trues and falses in the R column. P and not R, you need to do a little more. I have to actually look back and forth probably. So I need them both to be true, otherwise it's false, right? So P. Okay, but that one's true because they're both true. That one's false. And hopefully you guys are checking me. I think the rest are all probably false. Is that what people have? Yes, I got a couple of thumbs ups. Awesome. Okay, and then we need to OR these two columns together. So really it's, if we see a true in either place, then it's true, right? So true here. Actually, does someone want to be brave and read their column? I'll try to copy you. Volunteers.
Yeah, I can go.
Okay, great.
So we have true, true, false, then true, and then the rest are false.
And the rest are false. Cool. Is that what other people got? Awesome. Yeah. That's funny because I usually expect ORs to have more trues in them, but I think you're right that like down here, this is all falses down here, and this is and these last four are all false, and these last four are all false. So that makes those all false, and then we also get a false here. So yeah, so this is the way, and again, like this is sort of empty of content right now, so it seems a little bit arbitrary, but you just kind of see how the mechanics work, right? Any questions? Okay. So the much more interesting one is going to be implies. The imply, like P implies Q. So yeah, so hopefully everyone got this truth table, but I'll talk about implies for a few minutes just to give, it kind of goes back to what I was talking before about every time I go to Mars, I'm greeted by little green aliens. Let me talk about that for a few minutes, then maybe we'll take a break just to like talk about some of the grade scope and latex stuff, and then we can come back and do some more implication stuff. So implies, this is like the big one. So this is this is really if then. If P, then Q. That's really what implies. Like P implies Q. Like P logically leads to Q. If P is true, then Q is true. That's what we're talking about. It's an if then statement. So it's definitely more interesting than and and or, right? The notation, which I will use a lot, is this sort of double not headed, double boned arrow. It's this implication sign. So I don't think I was doing this when I wrote the proof of A times 0 equals 0 on Tuesday, but I could have been writing like this before every, from each line to the next, because that's what we were doing. We were using logical implication to sort of say each thing, right? So so what does this mean? This means the best way I've seen it stated is that is the following: whenever P is true, Q is also true. And in fact, that example I gave about every time I go to Mars, I'm greeted by little green aliens. I think that's actually fits into this, like, right? So like, if P is, maybe I should just write this way. If P is a statement, I go to Mars, and Q is a statement, I am greeted by little green aliens. Right? So those could be my P and my Q there. Then my claim was that whenever I go to Mars, I'm greeted by little green aliens. And the question of whether that's true or not was sort of a little bit vexed. And I think this is why. It's because like there's ways to determine whether it's false, right? So when is this false? It's false. I think even somebody said this earlier. If I go to Mars, but then I'm not greeted by little aliens, right? By little aliens. So I go to Mars. I go to Mars, which is P, and I am not greeted by little green aliens. I tried to write it out, so I'm calling them LGAs. And that is not Q, right? So this is false when you have P and not Q. But I think that means we can make a truth table like that's, and this is the only way it's false, right? It's like, that's what I'm saying. It's kind of like almost like a placeholder or something. It's like, you know, if I don't go to Mars, then it's Like, what does that mean? In fact, let's try to make the truth table and just think about this. Like think about it in this context, right? So or think about the context of this example. So again, we have our 4 possibilities: true, true, false, false, true, false, true, false. So if it's true, I go to Mars, and it's true, I'm greeted by little green aliens, then this is true, right? If I go to Mars and I'm not greeted by little green aliens, that's exactly the case when we said it's false. Yeah. So this was true. This was false. Now, the 2 that start where P is false are kind of interesting. Because it's like, if I don't go to Mars, well, I mean, maybe I stay on Earth, but I'm still greeted by little green aliens. Maybe they come to me. Or maybe they don't, maybe I'm not greeted by little green aliens, right? There's like 2 possibilities there. So, but this is what I'm saying is either way, because it's not falsified, because we haven't falsified the statement by giving an actual like condition of like, I go to Mars and I'm not greeted by little green aliens. This is where I'm talking, there's this slightly strange default towards true. So these are considered true. Right. So that's kind of, it's a little bit strange. It takes some getting used to, I think, that this is the truth table for implies, but it just kind of makes everything work in math. That's kind of one reason why we do this also. And I have read long philosophical articles about like why this is the right thing to do, but it's probably a little more than we need to do for this course, but it's an interesting thing. If you want to come debate it with me, you absolutely should. But yeah, like this is only false. This is only like false in the sense of being falsified, but given a counterexample in one scenario, and that's the scenario up here, right? And so you can actually see too, like I said, P and not Q. So if P is true and not Q is true, would make that true. And I said that's when this is false. So it's kind of the opposite of this. In fact, you could say that, right. So actually, let me just say this. I could do something here where I'm sort of like trying to combine this. This is like saying we can do P and not Q, but we really want the negation of that, because P and not Q is true if both of these are true, right? If both of these are true, then this is true. And that's the only case this is true. But here we actually want it to be false. So in fact, I want to put a negation sign there. And so there's another way to define the implies as not parentheses P and not Q. Hopefully this is obviously a not sign. Let me try to make it more obviously a not sign. Oh, that's not the right color. P and not Q. Okay, because if we actually build the truth table for that, I claim we'll get the same truth table. So I guess I mean as P implies Q. And you can do it. In fact, you should do it. In fact, I should let you get ahead of me and do it a little, do it yourself, and then I'll play catch up. So like, let's actually build the truth table for this. So not Q. then the next step could be Pn, not Q. I'm sorry, yeah, Pn, not Q. And then the negation of that, not P and not, well, not parentheses P and not Q. So build this truth table and see if you get the same thing as the truth table for implies. Give me a minute ahead of me. Wait, did my screen stop sharing? I looked at something else and I lost the share. Sorry, let me share again. Okay. Is it working out? Are you guys getting the same thing? Yes. Right, so not Q just flips this column. We and those together. The only place that's true, I think, is there. And yeah, and you can see it now that if you flip this column, it becomes the same thing. So yeah, again, a little strange, but this is the truth table for P implies Q. Yeah, okay. Okay. Yeah. So maybe we'll take a break just for a couple minutes. I just always, if we're in class and I'm going for like 85 minutes straight if I'm at the board, it just seems like really exhausting for everyone. So I often will give a break, but let's take a break for a couple minutes and we'll come back. We'll look at the grade scope and the LaTeX stuff for a little bit. And then will say a few more things maybe about logical implication just before we run out of time, but you should be, for example, well placed to do the problem set now, I think. Oh, yeah, the thing I need to talk about is contrapositive and converse, those ideas, and logical equivalence, but yeah. Okay, so let's take a break for a couple minutes and I'll even pause the recording. I have 10:57 now, so just like 3 or 4 minutes. I'll come back just after like 11. And someone remind me to unpause. Okay, we're back. So yeah, like I mentioned, there's this grade scope where you're going to turn your assignments in, which is over here. Now, the thing is, like, I can click on it, but then you're going to see it from my perspective, which is not at all what you see when you go, or you might see something kind of like this. In fact, I meant to see that. I know there's like a student. I thought there was a student preview thing, but I can't remember now how to get to that. But the point is, you're going to go to this and you're going to ask, you can like look at the problem set now. I have it I have it put so that like, right, there's the February 1st, 11 p.m., but then there's this extra time, like I said, built in. Again, it says late, but don't really consider it late, except I said, don't get yourself in the habit of using the extra time. And you're going to be asked to upload your PDF of your problem set. And one of the big things is that it asks you to assign pages to problem numbers. So if you have like, if your write-up ends up being like 4 pages and problem 1 and 2 are on the first page and you want to assign problems 1 and 2 to page 1, the reason is when the graders go through, when I go through and grade stuff, then it'll pop up right to the right place. Otherwise, we have to go searching through every time to find the right problem. Because when we grade, it grades like we grade all the number ones for everyone. And then we grade all the number twos. And so it's like you're grading the same problem. And it just ends up being super annoying if you don't do those assignments. And so in fact, the graders, I'll let them let you get away with it for like the first week maybe, but then after that, we just won't accept it if you don't assign the pages to problems. Do I say that actually somewhere here? Oh yeah, see, I actually said it here. It's important enough that I put it here. Yeah, so it asks you, I think the thing is that like it asks you to assign pages to problems, and then some students just skip that step or just quit because once they've uploaded it, they're done. But just don't do that, please. Okay, so that's grade scope. You should look at it, you should click on it from your end and see what it looks like for you. But it should be fairly straightforward. I've had students seem to understand what grade scope's about, but feel free to email me, or if you have questions, bring them up anytime. Okay. And then the second thing I was going to mention was LaTeX. So I did add those LaTeX resources. So LaTeX is the mathematical typesetting language. It can be a little intimidating at first. So I do have this page that I've written and updated over time about how to get started. In fact, it used to be how to obtain for your computer was first, and then the cloud stuff came along, but now it seems like most students prefer to do the cloud version. You can download it to your computer and do it all on your computer, which is what I do because I'm old. But there's this overleaf. So if I go to overleaf, I guess I'm logged in already. So yeah, because I was playing with this the other day. But so what I did is so back on the assignments page, there's the PDF of the problem set. There's also this file called the text source, and it's a .tex file. And you want to download that. And it's just like you can any text editor could read it, but you either need like a version of tech on your, and yeah, it's not pronounced text, it's pronounced like tech. You need either version of tech on your computer or you can upload it to the cloud. So like there's this upload button right here where it's like you can, upload a file. And so you can upload that .tex file, and let me make this go away. And then you end up with this thing here, which is this. Let me drag this over for a minute just to make this a little like more prominent. So this is what this is what a LaTeX file looks like. It's all this crap, but there's a lot of crap at the top, which is this preamble stuff, which you can just steal mine and just use mine. So you pretty much can just ignore it. Everything above is called the preamble. And then it's only when you get to begin document that you actually start making the actual stuff you see over here on the right. And so this is the PDF that it makes. So I'll go back through it all a little more, but like just as a place to see like let's do like even here you see like LaTeX instructions, and then over here you see LaTeX instructions, and so that's the corresponding thing, right? And there's even a command so a lot of commands in LaTeX are use backslash. So \textbf makes this bold over here. \LaTeX actually makes the little fancy LaTeX. Oh, you know what? I think there's a way. Hold on. I'm going to do something random, but I'll come back to this too. But I'm going to use the my browser's PDF here because I think I can make things bigger. Yeah. Okay, so like, yeah, where it says LaTeX, and so there's a fancy way to write LaTeX that you can do. So there's actually a command for that. There's also a fancy way to just write tech. So you can do a command for that. But like the real thing is when you get down to math, right? So if I scroll down here, oh, that's, yeah, okay. So these were the questions from the book. But then axiomatic proofs. so I've got a lot of comments. Everything after a percentage sign is a comment. Oops, sorry, somebody's asking me if we have to use LaTeX, that you can use Markdown. Actually, yeah, some students you can use Markdown if you want. There's because it's actually got LaTeX kind of inside it, I think, some Markdown stuff. So so there are other options now, like even in this Notion, I can type math in our website, I can type math, but it's still like a lot of the same commands as LaTeX. So it's probably worth learning. And if you're going to do any sort of real technical writing in the future at some point, like it's good to learn this. That's one reason we were making you do it in this class, is because it's a good skill to have. Like I have no people who write like econ papers in LaTeX or chemistry papers in LaTeX and all this stuff, you know? So anyway, so percentage sign just means anything after it's a comment. So you can see here, this is where the real math comes in. So like math is between dollar signs. So anything that you want to, like, basically the dollar sign is like a toggle between text mode and math mode. So you can, so I have this like slightly fancier looking ABC in the integers, and it's over there on the PDF, and over here it's just between dollar signs. And I guess I say that down here in the comment. So yeah, and then there's like the implication symbol, which we just talked about, is actually / implies, which is convenient. There's yeah, for every A and Z, -1 times A is -A is right there, and then that comes out like that. Again, you can see that the math is between dollar signs. /Z makes the fancy Z that I like, what I call the Blackboard bold Z. Actually, that's not what the command normally is to make that Z. Up in the preamble, you can like do commands. So the real command is math Blackboard bold, like math. That's what the math BB. So / math BBZ. But because I use it all the time, you can define it to be a shorter string, so I don't have to type / math BB every time. I can just type /Z and get the same thing. And here's like the rationals and the reals and the complexes and n's and natural numbers, just the positive whole numbers. And I have some other things that I've just thrown in here. So again, like I said, the preamble is not that important. Going all the way back up, there's like the document class, which is kind of just like the overall formatting, and you can change that to different ones. There's like, you can like Google that. And then there's all these packages you use, like to get most of the symbols you want. There's this package called AMS symbol or AMS sim, and then there's other packages that do different things. Like I said, more symbols. There's this math drawing thing called ticks. Colored text, I like to make things blue and red and stuff. So none of this is that important. And in fact, like I said, you can just take my LaTeX file, this tech file, upload it. Yeah, again, all this stuff is kind of random. But I did comment it all, so you can look through and read the comment. There's the headers and footers, which are like these things at the top. Yeah, please, Lauren. Oh, I can't hear you. Are you talking?
Sorry about that. So when I'm trying to upload the TEX file to Overleaf right now, and when I say upload project, it asks me to upload a zip file, and it says that the TEX file is invalid. I realize I might be doing it wrong. I'm curious if there's a special way that you uploaded the TEX file.
Oh, so let's see. There's this.
Mine looks different, huh?
Your looks different. So like, I think if you start a new project, I think what you have to do maybe, okay. So here's like the project. So if you actually start a new project and just like give it a name,
I see,
and then go to the project, it'll give you like, in fact, I think, right, it gives you this main.txt file that is just a basic file, and then you can upload. So then I uploaded this.
Okay, great.
But you're right. You're
what
right.
I was doing wrong. Yeah, I was.
No, that's a good point.
I was trying to upload a new project instead of a file.
Right.
Project.
Right.
Thank
No,
you.
that's a good point though that I didn't bring up, which is that like these things, everything's in these projects. So I just made a project called Math 2020 Problem Sets. And then it's like, yeah, so you have to make a project first. And I did that. I made a new project called that. And then when you do it, now you can have files. You can have a bunch of files over here on the left. So you could like have all your problem sets over here. And just I'll have it within one project, but then you upload right there. So yeah, good. Thank you. Thank you, Lauren. Yeah, you have to get used to the interface a little bit. I still do it on my own on the computer. Then I can do my math typing on airplanes when I don't have Wi-Fi. Or wherever I am. So okay, so yeah, like let's see, what else was I saying here? So right, so there's all this header, there's all this stuff in the preamble, which is not that important, except you can make like the headers and footers. And you can change these if you want. Like I think I said something like, oh yeah, maybe replace the prof king with your own name or something like that if you want. Begin document. The stuff at the top, which is like problem, this stuff says like problem set 1, all this, that's done. You can center text by, like, there's a lot of things, like a lot of the text formatting and stuff is not that important. It's really the math that you need to be able to put in here because you can just type and then put the math in between. But like if you want centered text, you can basically use begin and end center, and like everything between those will be centered. And then you can change the size of text by using backslash like large or stuff. Again, bold, blue. I like to make certain things blue, so I have these colors. You can force vertical space, like I want a little space after the, so there's commands for that. So there's a lot of, like, again, there's a lot of stuff, but the main thing is that you can just use my template and go through, and like I said, you can uncomment this, like here, like section, like so like after, so if we have section 1.1 number 4 here, and I could, after that, I could uncomment this, which is like just delete the, oops, deleted the letter A, delete the percentage sign, and then recompile, and now it says like, yeah, you can see it says answer down there. So then you could like put your answer, you can just kind of start putting your answer there, and some of the stuff you're just typing, you just type, paragraphs of sentences and stuff. So, oh, sorry, another chat. Oh, I was asked, are groups allowed to work on the same LaTeX document working on homework? I would rather you do your own homework. Like I like, obviously I encourage students to talk and work together, but making your own like final thing that you turn in, I say do not do that. Do not just like share, like just share your code with each other and stuff, because I want everyone to like kind of produce their own homework. I could have had group problem sets, and some classes do that, but I don't know. I tend to like to give everyone a chance to write out their own stuff. Okay, so yeah, so I have comments about, I just have this really heavily commented. There's numbering, you have this automatic numbering, like 1, 2, 3, 4, 5, 6, 7 down here. And I actually wrote these commands like resume and pause numbering, or pause enumeration. Because I don't like the way LaTeX has it built in of like, if I want to like leave the numbering and write some other text and then go back to the numbering, there's ways to do it. I just wrote this thing that does it. So just be a little careful. But then, so everything's after this backslash item gives you like the number 1 right there. And then it just keeps track of the numbering for you. Yeah, you can use, I mentioned the QED symbol. You can put in the QED symbol if you want. Oh, actually, I didn't even notice that LaTeX. I mean, this is, Overleaf is pretty good at like doing predictive text and stuff now also. So, so now if I recompile that, wait, does it have the little QED symbol? Wait, you guys are in my way. Yeah, so that little box is there now at the end of the proof if you do backslash QED. So there's stuff like this. I don't think it's too bad, but hopefully you'll yeah, I mean, you can get into crazy stuff with tables and stuff like that. And then there's all the like, where is this? Yeah, so tables are kind of crazy. I did comment it so you can see, but I also think I said at the top of the file that if you want to do the tables by hand and just include photos of them, that's fine. Because I know that's a lot to ask to make you guys make these tables like on your first problem set. So you don't have to do that. Although you should fill in, I think for number 3, you can just fill in this one. It's not too hard to figure out how to fill these in between these ampersands over here. Okay, I mean, yeah, maybe it seems like a lot and I'm making you drink from a fire hose right now, but it's not that bad. The one last thing I'll say is that, yeah, you can read all that, but like, oh, and I didn't upload the image, but if you want to include an image, why is this all, why is that all yellow? I don't know why this is all yellow. It's probably Overleaf telling me something, I'm doing something wrong. But yeah, so like you can include an image. So if you like scan, like if you make the truth table by hand and scan and like take a picture of it with your phone or something, or scan it, then it's really pretty easy to include. You'd have to upload the picture into this, and then this command and / include graphics, and you can set the width, and then you just put the name of the file, and it'll like put the picture there. So that's not too hard either, I think. I think in the actual PDF from the homework, I didn't, let me look at it here. Yeah, so I just like wrote that down and then took a picture of it and then put it there. So I didn't actually upload this file into Overleaf though, which is why it's not showing it in Overleaf. So, oh, I have this, oh man, this code was, I think I changed this, oh, you know what, this is probably because I added, so you have to be careful because when you add stuff will get pushed on the next page and everything like that. So these problems are going to be fun, you can tell. But I guess because I added the proof in here, I can answer stuff that's made it a little bigger and it pushed some stuff to the next page. Anyways, okay, does that make some sense? Yeah, decent sense. Okay. So just play with it. You can come to office hours, you know, again, if LaTeX is your issue and you need to turn it in a day late or something, then that's fine. Like I said, Gradescope will have that built in where you can submit stuff late and I won't penalize you for it. But just start playing with it and see if you can make it work. All right. Okay, just because we only have 10 minutes left, and I did want to talk at least about the contrapositive and the converse, because contrapositive comes up on the problem set, and they're just important concepts. So let me just jump back into the iPad. Okay. So contrapositive, this is just an important concept. Well, so we have P implies Q. Now that's kind of like one of our basic logical connectors. There's some other related statements. There's what's called the converse, which is when you just flip. You say Q implies P. Okay, and so again, think about the example we had. We had, if I go to Mars, then I am greeted by little green aliens. You could switch it around and say, if I'm greeted by little green aliens, then I go to Mars. Notice that's not the same statement. It doesn't have the same truth value necessarily. It's not equivalent to P implies Q. Maybe it's true that every time I go to Mars, I'm greeted by little green aliens, but if I'm greeted by little green aliens, it doesn't mean I'm necessarily on Mars. Maybe I went to Saturn and I'm also greeted by little green aliens or something, right? So so they're not the same thing, and that's an important thing, and not to swap your if. Basically, you're swapping the if and the then, and it's not it doesn't preserve truth value necessarily, right? So that's the first thing. So the converse is just flip, yeah. Q implies P. The contrapositive, though, is interesting. And again, with the example, I think, let's look at this example again, right? We said if I go to Mars, or if I, maybe I'll just say it a little bit differently. If I am on Mars, then I'm greeted by little green aliens. Little green aliens. What if I'm in a situation where I'm not being greeted by little green aliens? What can you tell me? Assuming this is true. What if I look around and there's no little green aliens greeting me? What can I say? What do I know is true?
Assuming that the first statement's true, you know you're not on Mars.
Yes, assuming this is true, then if I'm not greeted by little green aliens, then what?
Then like you're not on Mars.
Then you're not on Mars, right? Right, exactly. Like, then I must not be on Mars, because if I was on Mars, I would definitely be being greeted by little green aliens. So if I'm not being greeted by little green aliens, then I must not be on Mars. Yes, good, thank you. So right, so if so again, this was, let me just put this schematically, this was P, and this was Q. So if I am not being greeted by little green aliens is now the strange, it just sounds strange put out of my mouth. If I'm not being greeted by little green aliens, then I must not be on Mars. Remember, if I am being greeted by little green aliens, that doesn't force it to me I'm on Mars. They could have come to me on Earth. I could be on Saturn. But let's think about this statement right here is not Q, and this statement right here is not P, right? So in fact, yeah, the contrapositive of PM, this is called the contrapositive, basically negating the second thing and putting it first, or negating both and switching, I guess, negating both and switching, right? Switching the if and the then. Yeah, this is called the contrapositive. Called the contrapositive. And so if we have P implies Q, the contrapositive is not Q implies not P. And they are logically equivalent. They're the same thing. In fact, you could check the truth tables, right? These are logically equivalent. The converse was not, but the contrapositive is. And just as a quick check, again, let's write, I don't really need to make these so fancy. Let's just write these down to remember, and then let's write not Q, not P, and not Q implies not P to see that we get the same thing. right? So true, true, false, false, true, false, true, false. Sorry, I let you get ahead of me, but we're going to be out of time in like 3 minutes. So I just want to. So we said this truth table was true, false, true, true for P implies Q. So if I negate Q and I negate P, and now I do the implication, the only one that's bad is when true implies false, right? True implies false is the only way you get false. But if you negate both, you get the same thing. You get true implies, well, yeah, it's in the same location, I guess is my point, right? It's both in the second, they're both in the second row. So false implies false is true, true implies false is false, false implies true is true, and true implies true is true. And so these are the same. So you can sort of prove that they're the same. And in fact, we could write, let me just say this as one last thing, because I think it does come up on the problem set briefly. We could write P implies Q, not Q implies not P. And we can actually put, there's another symbol we could put in between, which is a double-headed double arrow. And this is the logically equivalent symbol, which is basically means they have the same truth table. Okay, if that makes sense. I mean, it also means like A, I'm just using A and B to use different letters. Like we say A if and only if. Again, just some language things. We say A if and only if. B. Actually, a lot of times we write IFF for if and only if. And there's even a truth table for that. Like it's sort of like basically it's basically if they're both true or they're both false, which I don't think we've seen this truth table, true, false, false. I'm sorry, wait, I did the same. I read the same column twice in my haste. True, false, true, false. So that is the truth table for that, because they're basically, if they agree, it's true if they agree. So the question or just an adjustment to the, okay. Yeah, and so it also means basically you could also, this also boils down to A implies B and B implies A. Right. So, okay. So that's logical equivalence. But really, if you end up with two columns the same in the truth table, then that you can tell the two things are logically equivalent, like up here. All right. Oh my God, I'm going over time. Okay. So I have office hours this afternoon at 2:30. I'll gather. Feel free to come talk to me. And class Tuesday back. I have office hours, a bunch of office hours, a couple office hours Monday, and then class in person, hopefully, unless we hear different, on Tuesday in Searles 113. So awesome. I will see you guys soon.
Thank you, Professor.
Thank you.
Thank you.
Yep. Take care.
Thanks.
It's the same Zoom link, right? For the next
All right.
class.
Say it again.
It's the same Zoom link for the next class, correct?
We'll be in person, hopefully, right?
Yeah, for linear.
Oh, yes. That's right.
Okay. All right.
That's right. I'm going to step off for a few minutes, but I'll be back. Yep. See you.